this economy, each and every household seeks to maximize its lifetime utility subject to its budget constraint. So let's assume the following utility function. So each and every household gets utility from consumption, and this utility from working. So in period time t, at any point in time, household seeks to maximize expected lifetime utility discounted such that the income generated from providing hours plus the return on capital equals expenditure on consumption and investments in next period's capital. So the first thing that we have to do is that we have to write up the Lagrangian. So we write up the Lagrangian. T equals 0. And then we write up the utility function, log of Ct minus Nt to the power of 1 plus sigma minus the lambda and then the budget constraint, which is Ct plus Kt plus 1 minus the wage generated from providing labor and the return on and the income generated on providing capital. 1 plus r t minus delta. So here we assume that in each and every period some capital depreciates. So now we've written up the Lagrangian, and this here is a kt. For some reasons this t dropped out. So the first thing that we have to do is that we have to derive the first order conditions with respect to Ct, Nt, and Kt plus 1. So differentiating Lagrangian with respect to Ct, we get beta. So we have to differentiate all of this here with respect to Ct. So log of Ct differentiated, we get 1 over Ct minus Ct differentiated, we get minus lambda. This should be equal to 0, and then we divide both left and right hand side with beta to the power of t. So we get that 1 over Ct is equal to lambda. Now we have to find the first order condition with respect to hours worked. So differentiating the Lagrangian with respect to Nt, here we take down the exponent, subtract 1, so we get Bt. Remember, Bt, the discount factor, is just a constant that is multiplied on all of this differentiated with respect to Nt. So we get minus Nt to the power of sigma. This one differentiated with respect to Nt is minus Wt minus lambda t. We get a plus lambda t Wt, which is equal to 0 because we're maximizing. So we get that Nt to the power of sigma is equal to lambda t Vt. So now we got the Ct, we got the Nt, now we just missing one first order condition. that is the more tricky one, is the kt plus 1. So here we are differentiating the Lagrangian with respect to kt plus 1, and we set everything equal to 0 because we're maximizing. So all of this differentiated with respect to kt plus 1. So this here inside differentiated with respect to kt plus 1 is a 1 minus lambda times beta to the power of t. So we get minus beta to the power of t times lambda. Then there is also a kt here. So now what we have to do, we have to forward this one period. So such that this one becomes a plus 1, then we have a plus 1 here. So we get minus lambda beta. So kt plus 1, we get 1 plus rt plus 1 minus delta. Differentiated, we get this thing here. The effective return rate on capital. And then we have a minus lambda. So we get a plus beta. Remember, it's to the power of t plus 1 because we are forwarding everything. And since this maximization problem is taking place at time t, we get lambda t plus 1 and the effective return rate on capital. And all of this should of course be equal to 0. So now what we can do is that we can divide both terms with beta to the power of t. So we get that lambda is equal to beta. Then the expected plus 1 minus RT plus 1 minus delta. So now we have found all our first order conditions. So in order to derive the Euler equation, we need to combine this first order condition here with this first order condition here. So we have that. So we know that lambda, it is equal to 1 over ct. And we also know that lambda is equal to beta, and the expected t plus 1 plus RT plus 1 minus delta. So substituting in, we get that 1 over ct is equal to beta 1 over, so lambda t plus 1 must be 1 over ct plus 1 times the effective interest rate or return on capital, where we take into account that in each and every period also some machines, some capital vanishes. So here we have the Euler equation, which basically measures the substitution effect, captures the substitution effect between consumption today and consumption tomorrow. So consumption at time t and consumption at time t plus 1. So let's imagine that RT, that the interest rate goes up. So let's assume that this one RT, that the interest rate goes up. So what happens is that consumption today is relatively more expensive. So households would prefer to increase its savings due to the higher interest rate slash return on capital. So as the interest rate, as the return on capital goes up, the households would like to take advantage of this higher interest rate. And how does this household take advantage of the higher interest rate? So remember, in each and every period, the household provides both capital and labor in order to generate any production in this economy, okay? So what is going on is that, okay, the return on capital goes up, so the household would like to take advantage of the high interest rate. How does it do that? Well, it increases its savings. So as the interest rate goes up, the right-hand side of this equation, Euler equation, goes up. Also, the left-hand side must go up. So a higher interest rate, the household would like to increase its savings because savings is now generating a higher return. How do I increase my savings? Well, I increase my savings by reducing consumption today. When I reduce my consumption today, the marginal utility of consumption today goes up and the equality sign holds. So this is basically the Euler equation.